Thank you, Dr. Goggins, and thank you for inviting myself and Megan to your conference this morning.
Are you hearing it
So I'd
okay?
like to talk briefly about historical silica exposures in Ontario hard rock mines. So we're going to look at measuring RCS, early methods like conimeters used to count total particles, and then in later years, size-selective gravimetric sampling in units of milligrams per cubic meter, and the challenge in converting ppcc's or particle counts into gravimetric and vice versa, not as easy as you might think. Also looking at what data is available to estimate historical exposures to RCS. Sources such as MAPAO annual reports, surveys by Ontario government agencies, Ministry of Health, Ministry of Labour, and more recently, the Ontario Mining Exposure Database, or OMED. I'm going to give you an example of using OMED data to estimate cumulative RCS exposures for a case series of miners with sarcoidosis that we studied at OHCOW. And then Megan is going to give you a brief overview on the Ontario Silica Control Tool. As most of you will know, respirable crystalline silica, or RCS, are the particles that are small enough to reach the alveoli of the lungs, so generally 3 to 5 microns or micrometers in diameter, and are associated with long latency diseases like silicosis, scarring of the lungs has been known for a long time, COPD, and lung cancer. It was thought for many years that lung cancer had to be preceded by silicosis before you could have lung cancer. However, it was found in later years that it's a direct-acting carcinogen, and in 1997, IARC classified RCS as a Group 1 known human carcinogen. So when we get into measuring dust and RCS, in earlier years, there was an increasing interest in understanding the relationship between RCS exposure or dust exposure in general and health effects on the lung. And one of the instruments that was developed was a conimeter. And I've got an example of one here, and I apologize for the poor quality and the kind of small text here. But essentially, it's an instrument that's, I'm going to guess, about 6 inches tall by about 3 inches wide. It's handheld. So it's a spring-loaded piston that draws a fixed amount of air through the chamber and deposits the particles, in this case, instead of an individual glass slide, onto 29 individual samples on a glass impaction plate, and then the particles can be counted under a microscope. The unit of measurement is particles per cubic centimeters, or ppcc's, and conimeter measurements were generally used to measure the effectiveness of ventilation in the mines, not necessarily to evaluate personal exposures. In later years, as there was a better understanding that mass, or the weight of particles, was more important than the number of particles in developing disease, size-selective gravimetric samplers were developed. So, and most of you will be familiar with this setup, where you have a battery-operated pump that can be clipped on a worker's belt, and then this filter assembly where you have a cyclone that separates out larger particles, and then you can collect various fractions of the smaller particles, in this case respirable particles, that are collected onto a filter that is then weighed to give you the mass, or milligrams. You know the volume, so that gives you milligrams per cubic meter. And then you can do X-ray diffraction analysis or other analysis to determine the percentage of respirable crystalline silica. This is obviously a much better setup for collecting personal samples, because the samples are collected in the breathing zone, and it's a very portable. As more studies were done on the health effects of respirable crystalline silica, RCS, it became important to be able to convert particle counts in ppcc's to the gravimetric measure of milligrams per cubic meter of crystalline silica. And there were different approaches and theoretical discussions on coming up with a conversion factor, and it was never really an agreed upon approach. So as part of the large study that was done by McMaster on silica exposure and silicosis in Ontario miners in the late 1980s, David Verma and his crew did side-by-side sampling of kinemators and gravimetric samplers, collected a large number of samples, as you can see here, about 2,400 filter samples and 90,000 kinemeter samples over 2 years in gold and uranium mines. So they had a pretty good data set and were able to develop quite an accurate conversion equation. And from that equation, they were able to develop a conversion table that was a little easier to visualize the relationship between the particle counts, PPCCs, in gold mines, nickel or uranium mines, with the corresponding concentration of respirable silica, and then from that, the respirable dust based on the average silica concentration that varied in the different mine dusts. An important thing to note is that there's not a linear relationship between PPCCs and milligrams per cubic meter. A small difference in particle count can make a big difference in respirable dust or RCS concentrations. So for example, for gold mines, just a small difference going from 489 to 523, a difference of only 34 ppcc's, results in a doubling of the respirable silica concentration or the respirable dust concentration. Now that we've had a little bit of history on the collection of particle counts and gravimetric samples, let's look at data sources that are available to estimate historical RCS exposures in Ontario mines. One of the main sources is the MAPAO, the Mines Accident Prevention Association of Ontario, and they were in between 1955 and 1982. Ontario mining companies submitted quarterly or semi-annual forms to MAPAO that recorded dust particle counts collected by kinemeter at different locations of the mine, usually by mining engineers. MAPAO then turned around and provided summarized data back to the mines so that they can compare how they were performing to similar mines. So for example, their gold mine, how they performed against other gold mines. And MAPAO also provided summarized data to WSIB for compensation purposes and MOL for compliance. So here's an example of an MAPAO semi-annual survey report form. So on the left, you'd have all the different operations that they could sample. So drilling, loading, filling, timbering, pulling chutes, mucking, and so on. They'd record the number of samples collected at each location, the average particle count, and then at the bottom, the overall particle count for all the operations that would represent what the average was for that particular mine at that time. So this would be April 71. They would also record the number of samples in different ranges. And this was important because 0 to 300 would indicate that these samples were below the MAPAO guideline for gold mines, and those greater than 300 ppcc's obviously above the guideline. And in this case, even though the average, overall average, is pretty close to the MAPAO guideline, almost half of the samples were greater than 300 ppcc's, and we'll come back to this a bit later. And also they recorded how many were in greater than 500 ppcc's, because the WSIB policy for gold mining and lung cancer has a definition of dusty gold mining that is 500 ppcc's. And lastly, they would record how many samples were greater than 800 ppcc. So that would indicate some pretty significant exposures to dust, because that's really the upper limit of kinemeter measurements. If we look at sources of sampling data available to estimate historical RCS exposures, to be quite frank, it was pretty skimpy or pretty scant for many, many years, because there wasn't a lot out there. The MAPAO did their annual reports, and so, for example, this is the data for 1958 to 1975, and this is an often reproduced graph to show the various concentrations in gold, nickel, and uranium mines, and showing the gradual decline and leveling off. And then they would also provide this table, again, you've seen in many reports, comparing the average dust levels in the first half of 1960 to the first half of 1975, Why they picked those years, I'm not 100% sure, but they were trying to sort of show that, or imply that, the concentrations or exposures were half of that in the later period than the earlier period. Two other sources of sampling data come from surveys that were done by the Ontario Ministry of Health in 1974 of uranium mines, but that particular survey wasn't necessarily done to collect an exhaustive number of dust samples, but was more to try out different types of samplers to see what would work best for mines. Because remember, this is the transition period, the beginning of the transition period, going from particle counts to gravimetric. In 1979, Ontario Minister of Labour did a more focused survey in gold mines, where they looked at different categories and tasks in 8 different gold mines. And overall, they found that although generally the exposures were below the OEL of 0.1 milligram per cubic meter, the maximum concentrations ranged up to 8-fold the OEL. So again, important to look at the ranges and maximum ranges and that sort of thing rather than just the averages. An important thing is that although these surveys were around and did provide some information, at least snapshots of what the exposures were in this time period, the information from those surveys wasn't available until much later, when Verma and colleagues published a couple of papers in 2014 and 2015 that summarized the results from these surveys. The most valuable source of sampling data that became recently available is the Ontario Mining Exposure Database, or OMED. In 2014-15, OCRC created the database by collecting over 120,000 sampling records on a whole range of different hazards for the period 1950 to 1999 from the major sources of the MAPAO that had data from 55 to 82, as we saw earlier, gravimetric sampling data collected by the MOL in the later years, from the 70s to the early 90s, and sampling data from individual mining companies. Now, most of the records are for respirable dust, RCS and radon, and about 4,200 RCS measurements are from gold, uranium, nickel mines, with most of the bulk of the data being from 1971 to 1991. In 2001, OCRC published an analysis of this data. And this slide shows you some general findings of that analysis. So the arithmetic means from 1971 to 1991 for overall and for the different types of mines for underground and surface are an interesting comparison, because it was thought for many years that surface miners didn't experience the same high levels of RCS exposures as underground miners. However, this analysis found that there was little difference, or if anything, in some cases, surface miners are exposed to higher concentrations of RCS. Also, and this is only a sort of a little snapshot of some of the data that's in that paper, although they found that the trend was decreasing concentrations of about 6% on underground and 8% in surface operations, they concluded there was still a probability of overexposure to RCS in Ontario mines. Now, this is proven to be correct in a very recent paper published by Victoria Arundale from OCRC that analyzed RCS levels for more recent data from 2014 to 2018. The results were surprisingly similar to this earlier analysis of data from 1971 to 1991. So again, indicating that there's definitely still issues around silica exposures in Ontario mines. OCRC was generous enough to share OMED with OHCOW and more recently with WSIB. And then Martin Albinger, one of the hygienists here at OHCOW, deserves a big shout out, because he did and continues to do a lot of work on OMED to make it user-friendly and searchable by a whole variety of different criteria. So mine type, or job title, task, location, etc., and built-in conversion of the PPCC to milligrams per cubic meters. And by using this data in OMED, it allows us to calculate the mean and range of RCS concentrations, and also, excuse me, also the cumulative exposures for individual miners. A limitation of the data, as with any database, is that it's not 100% complete. In other words, there's no way it can cover all mines, all jobs, all tasks over this broad range of time. So in some situations where specific information isn't available, like sometimes we're lucky, like, you know, if the miner worked in a particular gold mine, in a particular range of years, and that information is there in OMED, we can be very particular or more precise in the estimates. If not, then we have to kind of take a step further back, and let's say he was a driller in a gold mine, but there's no data for the particular time he was there. We then can take the data for all gold mines for that period and provide sort of a more general estimate of exposure. So here's a screenshot of OMED, just to sort of give you an idea what it looks like. And as I said, and I'm sorry the print is so small, but you can search by mine name, whether surface or underground, sampling year, exposure group, primary ore, type of hazard, and then, as I say, you can dice it and slice it any way you want, similar exposure group, sampling location, and so on. There's even a one-click converting to milligrams per cubic meter or ppcc's, because as in this case, in some of those overlap years, you have data that's in both units, and this way you can convert them all to one or the other. And in the earlier years, for example, it'll all be ppcc's, and you can convert everything to milligrams per cubic meters. There's also down here in the left lower corner, you can calculate some stats, which is always useful. And there's a lot of different things that you can do with OMED. So just to finish things up, I'm just going to give you an example of how we used OMED to estimate RCS exposures for a group of miners that were diagnosed with sarcoidosis. So within the McIntyre powder cohort of about 500 miners, there was about 12, actually more than that, because these are the 12 that were diagnosed with definite or probable. There was also a number that were diagnosed with possible sarcoidosis. But anyhow, this was a larger number than you'd normally expect. And most of the miners worked in different types of mines, gold, uranium, base metals, in a range of jobs, underground or surface, and for different periods. So again, the challenge was to try and assess cumulative RCS exposures for each of the miners. So here's part of the exposure table from the paper that we published on this, and you can see the three categories of mines: gold, base metals, and uranium, and all mining combined. There's different combinations of work histories here. So for case number 8, this miner worked in all three categories of mines. So we calculated cumulative exposure for each, and then the total cumulative exposure. In this case, these miners only had exposure in gold mines, and we would try and identify the major jobs that any of them had. And case number 11 down here only worked in uranium mines, and so on and so forth. So for each one, we were able to calculate the individual cumulative exposures for each type of mine, and then totaling it up for all the cases. Again, the mean annual exposure, and then the range, and then a total for the whole group. Here's a screenshot of the paper that we published on this case series, and Dr. Christine Oliver did all the medical work on this one. I did the bulk of the exposure assessment piece, and then we had contributions from other members at OHCOW. And this was an important thing to do because there's been some suggestive literature up until now of a relationship between sarcoidosis that in the past was always kind of considered as, you know, no known cause, and the WSIB would automatically deny those claims. So we wanted to add to the literature with this case series and hopefully further more research into this relationship between sarcoidosis and RCS. So just to summarize, we talked about measuring RCS, early methods using conimeters and counting total particles, and then later on size-selective gravimetric sampling, and the challenge of converting ppcc's to milligrams per cubic meter and vice versa. We looked at data sources to estimate historical exposures. It wasn't much early on. Things like MAPAO, surveys, a couple of surveys by MOH and MOL, but then in more recent years, much more information available through the Ontario Mining Exposure Database. And then I gave you a quick example of how we can use OMED data to estimate cumulative exposures. Now that I've told you about how we can estimate past exposures to RCS, Meghan will tell you about what you can do to identify, assess, and control current exposures to RCS using the new Ontario Silica control tool. Take it away, Meghan.
Great. Well, thank you so much, Paul. Hopefully everyone can hear me, and if not, just jump in and let me know. So here is the Ontario version of the Silica control tool. And what does it do in a nutshell? It is an online risk assessment tool to help any workers, employers, and companies in Ontario calculate estimated exposures to respirable crystalline silica. It's a free online tool, and it's available to all students, Joint Health and Safety Committee members, union representatives, workers, of course. And so it is, don't think that just because you are not working directly with silica, if you're interested in looking at the data that this tool contains, you're welcome to create an account. As you can see here, under the please select section, there are actually two versions of the tool. There is one that is geared towards Ontario construction. So it contains data primarily geared towards the construction industry. And then there is a surface mining version of the tool. So if you're more interested in activities like crushing, loading, material moving in the surface mining sector, that would be the version to select and move on. But I'd like to point out that there is information in both that can overlap at times. So don't just look at the surface mining tool, and if you don't see what you're looking for, it doesn't mean that it's not potentially represented in the construction version of the tool. Next slide, please. So here we have just a couple of examples of, before we take a look at the tool, what is the tool going to prompt you to ask? It's going to ask you for, basically it has drop-down menus. It's quite easy to use. It's going to prompt you, the user, with basic questions of job sector. Are we looking at commercial, residential, mines, pits, and quarries? It'll ask you questions about the project type. Are you working new construction, renovation, demolition? Sometimes that applies in the surface mining tool, that selection wouldn't apply. And then it'll ask you to select the type of material that you or a worker is working on, meaning what silica containing material is going to be disturbed? Is it what's going to be moved or crushed or altered? So, for example, it can be rock, sand, and earth. It's also concrete is also a big selection within the construction version of the tool. Mortar, ceramic tile, plaster, shotcrete, amongst other things. Within the gravel, pit, and quarry, within the surface mining tool, your only selection will be gravel, pit, and quarry. It won't allow you to differentiate different types of ore at this point in time. Then the tool is going to ask you to identify the task or the work activity that you or the worker is going to complete. Is it grinding? Is it polishing? Is it crushing? Is it moving, drilling, or blasting? All of these types of, just to give a few examples of different types of tasks or work activity that's going to be completed. And then there's also tool selection as your last option. How is this work going to happen? Is it going to be with heavy equipment? Will it be done by hand, moving materials simply with shovels or by hand? Will you be using some sort of mechanized equipment like a crusher? It'll prompt you with drop-down menus to make your selection, and using that and a few other details such as work area and sort of the estimated duration of the task, it'll then calculate an estimated exposure value for crystalline silica air. So next slide, please. And on this next slide, we are going to see what are the best visuals within the tool. So for example, there are two, it's called the dial page, and this is where it provides you with an exposure analysis, assuming no controls. There's also an option further on in the tool to then have a recalculated exposure analysis with controls that you select within the tool, meaning controls like engineering controls. What we're looking at here, the top dial, this is a grounds person at a surface mine who is working at a crushing and screening plant for approximately 8 hours. So let's say that's your task, or that's your worker's task. Without having to go out and potentially hire a third party to complete hygiene air sampling, or completing the air sampling yourself. Sometimes you're pressed for time. This overall task of using the online tool takes about 15 to 20 minutes start to finish, just to give you an idea. This can help you give you kind of a good idea of the overall potential exposure for that worker completing a task. So for example, here you have this grounds person over 8 hours. Well, as you can see, the needle in this dial is sitting in the red zone. Red is not where we want to be. We'd like to see it in the green zone. But as compared to the exposure limit that is put into the tool for Ontario, we are in excess. This worker has the potential to be overexposed. And I would like to also point out that in Ontario, there are two exposure limits for silica. There is 0.1 for quartz silica, and then there is a 0.05 for cristobalate silica. The tool doesn't have the functionality to be able to choose between the two, and so as a best practice, the lower of the two OELs were selected to input the tool to be more protective overall for workers. Let's take a look at this lower dial here. Another calculation, a different type of material task and tool. This is an operator who is drilling rock with a drilling machine outside for less than 4 hours. So if that was my work activity or my worker's potential job activity, they are sitting quite far into the red, which is not where we want to be. And if you were to take a look at the columns here, it gives you an estimated exposure level of nearly 0.4 milligrams per cubic meter of air. And as you look over in the other columns, it shows you here as compared to the more stringent occupational exposure limit of 0.05, your worker has the potential to be overexposed by nearly 800%, which is quite a bit. That is fairly high. And there are times where this dial can go even higher depending on the type of activity, especially when a power tool is used. These estimated exposure levels will jump up quite a bit. And lastly, there's a little column for action level, the 0.025 milligrams per cubic meter. That is a best practice used by hygiene and health and safety practitioners. It's also gives you a potential to consider really the health, so the health-based exposure limit, and also the OEL used in British Columbia, for example, where this tool originates, they use a value of 0.025 milligrams per cubic meter. So it is another value to which we can compare this estimated exposure level. Next slide, please. And here we are for questions and comments. Paul and I are open to any questions you may have.
Okay, everyone, if there's any questions, you can leave them in the Q&A. I do have a question. So we do have a lot of students on the line here, and this is a fun tool to experiment with in a, like you suggested, in a way where students can explore how to do an evaluation without actually doing any measurements. So is there a video available? I tried to look through. Is there a video available for how to actually use the tool?
There is. I will, let me find that. In the meantime, I'll put in, if you'd like an account, there's a way to do it online, or you can simply email the Silica tool. It has its own website or email address, and I'll put that into the chat while I'm looking in the background for that video that would explain a bit further how to use the tool.
Okay, awesome. Yeah, because just to clarify, anyone can create the account. You don't need the WSIB number. Right on the front there, it says WSIB number. Is that something
Yes.
we need?
It does. It's a bit of that's a bit of a barrier. There's a workaround for it though. Basically, yeah, you just put in there's just a separate page that you click on. If there should be an option that says I don't know, or I don't have my WSIB account number, click on that, and that will take you to an alternative way to create an account.
Okay, awesome. Yeah, if you could get us that information back, and then we can hand it out or put it in the chat for everybody later this afternoon, just so you can get a hold of this tool. That would be great. Looks like we have the email as well. So Megan put it right into the chat. So email any direct questions about that or how to use it to Megan, please. Are there any other questions about the silica? I know we did a lot of respirable hazards this morning. Does anybody have any questions using their expertise here? What are the next steps with the exposure tool or the mining databases? Do you have any initiatives planned for the next 3 to 5 years?
It is. Oh, go ahead, Paul.
No, it's okay. Yeah, as far as OMED, and I should have mentioned that in the presentation, it's a work in progress. It's continually, new data is being added, and so for more recent years, there's data that's being added, so it's expanding all the time. And we're trying to develop, and I say we, Martin and other people at OHCOW are trying to develop it into an even more user-friendly. As you saw, the screen, it can get kind of busy and a little complicated on clicking this or that. So we're trying to make it a little more user-friendly. So now, how widely that's going to be available, I'm not 100% sure, because technically it was a property of OCRC and they shared it with us and with WSIB so far. I don't know that they've shared it more broadly. But anyway, so that's kind of from our end how we see it. And as I say, it's an ever-growing, ongoing work in progress, because right now, of course, we're still looking at exposures going back. We have some miners that still have exposures going back to the 50s and 60s, but as that slides along, the more recent exposures are going to become more and more important, obviously, as the years go on.
Okay, and there's a couple more questions here. Can you input extended work hour limits to compare it to when you use this tool? Yeah.
In the Silica control tool, you can.
Okay, so it doesn't just have to be the 8-hour limit. You can put the 10, 12.
Yeah, it has a little box that you select, and then you can put in any hours you'd like.
Awesome. And where is the new data for OMED being added from?
Well, it's again, it's from sources like mining companies. There's still records that are being I don't know that we have, even at this point, I shouldn't say, I keep saying we, I don't think absolutely all the MEPAO data is in there yet. Because initially what OCRC did, they literally had boxes and boxes and boxes of paper files, right? So, and that all had to be inputted. My understanding is that there's still, some data there's some records that haven't been completely added to it, but OCRC would have a better handle on that.
Okay, I think that's it for like our formal questions. Yes, that's it from both chats for our formal questions here for both of you. So thank you for the presentations in this session. So I think if I were to summarize both of these presentations, we are in the process from the OC Health and Safety side, it looks like, creating databases to interpolate large amounts of data from different sensors or sources to try and come up with bigger picture solutions, or let people estimate, because most people on the call here will know how expensive third-party